Alright guys, I hope that you will be able to see the screen, but it's not been an easy task to get the freaking markers to work. So anyway, well, with the camera anyway, I guess. So like I wanted to mention that I'm going to start doing video lectures for everything. So trying to figure out, okay, right there, about where I can write. Okay, I'm going to start doing video lectures so you guys can review them, and also so that Cameron doesn't have to teach, because I know he has another class. So hopefully this will make it easier for Rue to learn, and you guys don't have to teach him after I've already taught you, and so he can go to his class as well. Okay, so I'm going to start right now with inverse functions. I started to go over it on Thursday, and I don't know if you guys told Rue much about it, but basically an inverse function is defined by this set of functions. So if we have a function of x, there will be a inverse function of x. I'm going to denote it by a -1, such that f minus 1 of f of x is equal to f of -1, which is f inverse of x. Okay, and those are inverse functions of each other. Can you see that? Yeah, you can. Well, sort of anyway. I guess you're going to have to try and bear with me on the colors, because I'm not getting like a great camera out of my computer. So anyway, similarly we can say g of x is an inverse of f of x. If the same principle applies, g of f of x is equivalent to f of g of x, and that is all equal to x. Similarly, we can say that here it's equal to x. Okay. Now that's in our section for 5.3. If you're following along in the book, that is the definition of an inverse function. Okay. 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 So the way we verify an inverse function is by checking that when we plug in for a function that we in fact do get x out at the end, basically. So I'm going to go through example 1. It's the best way to do that. So f of x here is defined as 2x cubed minus 1. Okay, and g of x is defined as the cubed root of x plus 1 over 2. Is that visible? Yeah, it's fairly visible. Okay, so the way that you check is that we go and we plug in g of x for f of x. So basically, wherever there's an x, you replace it with the equation. So where we have 2x cubed minus 1, we plug in all of this in the x here. Okay, so let's do that for f of x. So f of g of x equals 2 of cubed root x plus 1 over 2. Okay, and all of that's cubed minus 1. Okay, so here we can obviously see the cubic here and the cube root cancel out, so what we end up with is 2x plus 1 over 2 minus 1. The 2's cancel, right? 2's gone, and then the plus 1 and minus 1 cancel, and we're left with x. Okay, so g is an inverse of x, and to fully prove it, we need to know that if we reverse this, where g of f of x equals x, or it should equal x anyway. So let's try and evaluate for this. we do the opposite. So wherever there's an x, we plug in this, okay? So here we're going to see cubed root x plus 1, 2. So we got to remove this. Let me plug that in. So we get 2x cubed minus 1 plus 1, right? Okay, so let's solve for that. We get the 1's cancel, okay, obviously, and the 2's cancel right away. So this is gone, and this is gone. So all we're left with is an x cubed root, and that gives us equals x, right? So that's not too bad. And obviously now they're inverse, right? We're getting the x out like we wanted. We can conclude they're inverses of each other. So that wasn't too bad. Erase that real quick. Book goes over kind of a definition of the inverse. It tells us that for an equation to have an inverse, it must be monotonic, and it cannot have multiple horizontal crossings. So what that means is it must be strictly increasing or strictly decreasing. So if we have a function f of x that we plot out looks like this. Okay, it's like, I mean, I didn't draw it perfectly, but you probably can't see that anyway. Yeah, it's always got either like a zero, well, I can't have a zero slope, excuse me. It always has a positive slope. It can also always have a negative slope. I just drew a straight line, but you can have anything that varies if you want. Something that has multiple crossings would be something like a quadratic equation. See, you can draw a line right here. We have multiple horizontal crossings. The y-coordinate you can associate with multiple, and when you can't have that for a function that has an inverse. So that logic can also continue with anything even order, so x squared or an x to the fourth. Those will generally have multiple horizontal crossings, because if you have something that is minus 1 to the fourth, or any even order, it's going to just be 1, right? So yeah, that's just something to keep in mind. So if you see an x to the fourth, it probably doesn't have an inverse. Okay, yeah, so let's keep going with some of the examples in the book. We will, okay, so example 2, we talk about like functions that have an inverse. So it asks what functions have an inverse. So we have f of x. The first one is f of x is equal to x cubed plus x minus 1, I think. Is that right? Yeah, okay. So the solution says, they show a graph, and it kind of looks like this. And from what we were just talking about when we graph this out, so that's something you can do on your calculator. You can plot this function over a certain domain and look, okay, well, for this range, it's strictly increasing, obviously, right? So knowing that, we can say, okay, well, it has an inverse function. That's great. So what does the inverse function look like? Typically, it's going to look like a line that, so let's draw the axes here. So if those are the axes, just bear with me, it probably isn't accurate. But, so if this is f of x, we have a line here. Okay, that's the y equals x line, or a slope of just 1. Okay, the inverse function is mirrored on this. So here we'll have something like that, okay? And this is f inverse of x right here, the one that I just drew, f inverse of x is there. So you'll see a mirror perfectly across y equals x, okay? So this one does have an inverse. if we draw differently, just erase the whole thing. So if we have another equation, x cubed minus x and plus 1, okay, that equation kind of looks like this, okay? What's the problem here? Well, we draw the axes. We have multiple horizontal crossings, obviously more than one location. So here we have like 3. Here, like at the top, we have 2. Doesn't really matter. It has multiple horizontal crossings, and it's not strictly monotonic. Usually those go hand in hand. I suppose, yeah, I mean, if it has it, yeah, so they go hand in hand generally. I can't think, I was trying to think of like an example that wouldn't be, but I can't, so anyway, obviously multiple, there's no inverse for it, okay? So now we're going to work at finding an inverse function. In the book they discuss guidelines for finding an inverse function. It's not too hard. Basically what you end up doing is you substitute y with x after you flip the equation. So I know that doesn't necessarily make sense in words, but let me go through the example in the book that they show. So they show f of x equal to square root 2x minus 3. Okay, so let's substitute y equal to 2x minus 3. Okay, so that's the first step. Substitute y for the function. Now what we want to do is we want to get x on a side by itself. So what we have to do, get rid of that. It gives us a y squared equals 2x minus 3, right? If we raise both to the power of 2, this will disappear, so that's what we get. So y squared minus, or plus 3, cancel out the 3 on this side, okay, equals 2x. Now let's have y squared plus 3 divided by 2 equals x, okay? That's what we want, okay? So now we flip the sides. We have x on one side and y with a bunch of other stuff on the other side. That's exactly what we want. So now all you do is you interchange x and y, okay? Now follow me here. It's y equals x squared plus 3 over 2, okay? Now that's your inverse function, okay? And so this is f minus 1 of x equals y equals all that. Okay? And so now we can verify that. Let's do that real quick so we know, okay, is that what we're looking for? Okay. So let's plug in. We can plug in for 1 because if we plug in for 1 we know it's good. So let's do that real quick. So we have x squared plus 3 over 2. So let's plug in f of x. 2x minus 3 squared plus 3 over 2, okay? Okay, so this is obviously f inverse, sorry, the other way. F inverse of f of x. Okay, so it's not too hard to evaluate. Square root cancel, we get 2x minus 3 plus 3 over 2, right? And if we just look at that real quick, 3's cancel, the 2's cancel, we get an x. So those are inverse of each other, and that's how you find the inverse. Not too bad. Okay. This is a pretty short lesson, so I should be done pretty quick here. I'm going to try and shoot to get lessons that are about 20 minutes long. That way you guys have time to do homework afterwards or what have you. Example 4 kind of discusses more about the like one-to-one, but I mean, I think you guys can pretty much figure that out. So later they talk about the derivative of an inverse function.
Okay? So basically their theorem is that if f is continuous on the domain, then f inverse is continuous, and basically increasing, then f inverse is increasing, f is decreasing, f inverse is also decreasing, kind of what I just showed you with that flip across the x equals y axis. And lastly, it says if f is differentiable on an interval containing c, and f prime of c is not equal to 0, then f inverse is differentiable at f of c. So it's saying basically at any given point, if f is differentiable, then f inverse is also that. So the derivative of an inverse function, we have g prime of x, where g prime is the derivative of g. I know I use different notation, but let's stick with g prime being like the derivative, and the inverse has to have that -1 that I mentioned a little earlier. So g prime of x is equal to 1 over f prime of g of x. So, right? Yeah, f prime of g of x. Yeah, where f prime, where use an arrow, f prime of g of x cannot equal 0. Okay, so that's kind of the proof they talk about in theorem 5.9. Okay, so let's just write that up at the top so we can remember it. 1 over f prime g of x. Okay. So last thing I think I want to go over here, evaluating the derivative of an inverse function. If f of x equals 1 over 4x to the third plus x minus 1, they ask what is the value of f inverse of x when x is equal to 3. Okay, so let's solve for f inverse. Is that f inverse or f prime? F inverse, okay. So f inverse of x is equal to y equals to 1 over 4x to the third plus x minus 1. Okay, y minus 1 my apologies. Okay. Okay, so let's not actually fully evaluate it. Instead, let's plug in the value. Sorry, I was thinking it out and then I was like a little flustered. So instead, let's evaluate those values. So the solution says let's plug in x equals 2. Okay, so they want to know a f inverse of 3, basically. Okay. So they kind of use reverse logic. Sorry, I was trying to think of a good way to explain this. So they want to know when does f inverse of 3 equal something. So their logic, what they say, because f of x equals 3 when x equals 2, so if f of 2 equals 3, f inverse of 3 is equal to 2. So basically what you want to do to find this answer, this is the answer we're looking for, right? To find this answer, you set this equal to 3, and you find what x equals at that point. So that's basically the logic they used, and they said it kind of simply, but you have to go through the steps. I hope that makes sense. But I'll just do it real quick. So 3 equals
they want to know what 3 is basically. What does x equal at that point for this function? 1/4 x cubed plus x minus 1. Okay, so we get 3 plus 1 equals 1/4 x cubed plus x. And you have to solve for that. And so we get 4 equals 1/4 x cubed plus x. Okay, and solve for that. So since they said it was 2, like I'm trying to think of a good way of explaining it, but I guess that's the best for what they give us. So obviously we know it's 2, let's just plug that in. X 2 to the third is 8, so we get 2 plus 2, okay, equals 4. So that's right. Sorry, I'm having a little brain fart about how to evaluate that quickly. But that's the way to go about it. So we'll just stick with that now. So now we know the answer to A. Okay. So just remember this. Basically, you need to solve for the answer. So if we want to know what f inverse of x is, or f inverse of z, we'll call it, we need to know what x is equal to when f of x equals z. Okay, does that make sense? Sorry, that was a little confusing, but that's the approach. I hope that made enough sense and I wasn't just babbling. Okay, so they also want to know what f inverse of x is when x equals to 3. F inverse of x, yes sir. Okay, so the approach they take, f inverse prime, oh that's what I missed, f inverse prime, where that's the derivative, is equal to 3. We need to evaluate this equation. Okay, so yeah, okay, where g is the inverse of f. Okay, so f inverse prime of 3 is going to be equal to prime f inverse of 3. Sorry, the logic in the book is kind of strange because they jump around a little bit. And I'm feeling a little stupid right now. Alright, here we go. F. We get prime f inverse of 3. Okay. That's what we want to solve for. Here we have f prime, f inverse 3. Okay, so that's what we're looking for. That's the golden goose. Okay, so what that leaves us with is 1 over f prime of 2 now. Okay, so it kind of follows that same logic as before. So all we have to do is do 1 over the derivative. So we know the derivative to be 3 over 4x squared plus 1 cake, okay? So now we just plug that in for 2. 1 over 3/4 times 4 plus 1. We get 3 plus 1 equals to 1/4. And that's our answer. So, sorry if that was like a little clustery. I felt like I took a long time to explain that. But basically, follow the equation if that's what you need to do to solve for like derivatives. You didn't use the same notation. I hope that makes sense. So whenever I do these lectures, I want you guys to know you can send me like a Facebook message through that page and ask any questions you want. I'll be able to respond semi soon. If it's a Monday or a Wednesday, I probably won't respond really quickly, but I will have responded by like the end of the night. And obviously you have Cameron to ask if you really need to know. So we're going to try and get on schedule
where I give you this lecture Monday, and the homework's going to be due Tuesday. Okay, so yeah. So that's it for this lecture. The only other thing they mention in that chapter is the g of x equals, well, okay, so if you have an f of x and a g of x, where g of x is the inverse of x, they will have reciprocal slopes at any given point. And what that means is fairly simple, straightforward. It's just if you have an equation kind of like that x equals y line, so let's just use this equation. It's strictly monotonic. It is monotonous, but that's besides the point. Okay, if you have this x equals y line, you're going to have reciprocal slope. Okay, so you take the derivative at any point, like here. If this is, if they're exactly the same, I'm trying to, okay, let's just do it. We're taking the derivative at this point. If it is equal to, this is f prime of x, and it is equal to 3, then the slope at the same, at the y coordinate, like, okay, if let's say this is minus 1, 1, okay, the coordinate 1 of minus 1 of the opposite equation will have a slope of 1/3. Okay, does that make sense? I hope so. I need to stop asking that question because you guys aren't here to answer. So anyway, that's the idea, and that's something to think about. So get the homework done by Tuesday so we can grade it during class. We're going to have a crap load to grade now that I think about it, so I'll have to get here early on Tuesday. Okay, that's it for this one.